Good afternoon, students. Hope you all are fit and healthy at your homes. So, in our mathematics, before MST, we were doing our Laplace equation solution. So, till now, I had told you that you have to do Laplace equation in 2 dimension, the solution of this equation, then for 3 dimension, polar coordinates, cylindrical form, and spherical form. And I also told you about the polar coordinates, cylindrical coordinates, and spherical coordinates, right? And this one I told you to do by yourself. This one we had done in our lecture. So today we are going to find out the solution for this, the Laplace equation in polar coordinates. Okay. So this is your equation, Laplace equation in polar coordinates. You know that your polar coordinates are r comma theta. So here the equation is r square curly square u over curly r square plus r into curly u over curly r plus curly square u over curly theta square equals to 0. Okay, here u is a function of r and theta, and we have given this equation as number 1. Now, as we were doing earlier, we will assume that the solution of this equation number 1 is of the form u is equals to capital R, which is a function of r only, and capital phi, which is a function of theta only. Okay, so we have assumed that u is equal to this, right? Now, substituting this in our equation number 1 as we were doing earlier, so we have to find out the value for curly square u over curly r square. From here it will be r double dash into phi. Curly u over curly r will be r dash into phi. Curly square u over curly theta square will be r phi double dash. Right? So by this way we have written our equation. You know this method, you have done this to find out the solution for your heat equation, wave equation, then Laplace equation for 2 and 3 dimension. Okay, the same method of separation of variables. Fine. So now we have written it like this. Now what to do? We have to separate the variables. For example, look for these two terms. The phi is common, so we have taken it out. Then what is left? R square r double dash plus small r capital R dash. This term as it is equals to 0. Now what we have done? We have shifted this term to the right hand side. Then we have separated the variable. The phi shifted to this side, the r shifted to this side. And this way it becomes, right? Now clearly the left hand side is a function of small r only, because this capital R is a function of small r, right? And this right hand side is a function of theta only, because this phi is a function of theta, right? So now this is your equation number 2. Now the left hand side is a function of r only and the right hand side is a function of theta only, and they are equal, but r and theta are independent variables. This implies this equation will hold good if each side will be equal to some constant k, right? So second holds good only if each side is equal to some constant k, right? Now from second, once we will equate this term to k, then we will equate this term to k. So we will get two equations. One will be this term equal to k, second will be this term equal to k. So we will get this one. The equation number 3, from where we got this equation number 3, when this will be equals to k, this capital R can be shifted to this side, this term will become, right? And this small r square and capital R double dash. Capital R double dash can be written as d square capital R over dr square plus this small r as it is. Capital R dash can be written as d capital R over dr equals to, it was r into k, we shifted it to this side, it become negative, equals to 0. So we gave it equation number 3. Similarly for this one, first of all shift this phi to this side, then this phi double dash can be written d square phi over d theta square, because this phi is a function of theta. Then when this phi k will be shifted to this side, both will be having negative sign. So negative sign can be taken out common and shift it to right hand side, so we will get this equation. Right, now we have to solve these two equations to find out the solution. Now for this equation number 3, look at this equation. You have already done an equation, that is Cauchy's homogeneous linear equation, in your ordinary differential equations chapter. Right, now this equation is similar to that one. This equation is similar to Cauchy's equation that you have done in your ODE, ordinary differential equation chapter. Right, now in that equation what was given, that equation was like this: x, if I talk about second order, x square d square y over dx square plus x dy over dx plus y equal to a function of x. So the degree of this x and the order of this derivative were same here also. Right, now the same thing is here: r square second order multiplied r raised to power n 1 multiplied with the first order. So this equation is similar to this Cauchy's equation. How we were finding out the solution for this? Here we were putting x equals to e raised to power t. Right, so similarly here we will put this small r equals to e raised to power z. Here we were taking t, so here we have taken z. Okay, so in the same way, when you will put this when you will do the substitution in this equation number 3, this equation number 3 will reduce to this one. The variable small r will change to small z, as here the variable x was changing to small t, the x was changing to t, so here the variable is changing from r to z. So the equation will become this. Okay, now for this equation you know that how to find out the solution. Now we have these two equations, equation number 4 and equation number 5. Again we will assume the three cases: when k is positive and equal to p square, when k is negative and equals to minus p square, and when k is 0. So you know it better how to find out the solutions by taking these cases, as we have done it in so many solutions. Right, so first of all, when you take this k positive and equal to p square, so you will get your solution for capital R and capital Phi in this form. Okay, solve it. If you will be having any problem in this, you can tell me. I will tell you how to find out the solution. Okay, when k is negative and equal to minus p square, you will get the solution for capital R as this and 5 as this. Okay, then when k is 0, you will get these two solutions. Now in this case, this equation number 5 was reduced to z. The variable r was substituted as z. So we got the solution in z, but we need the solution in small r. So here we will do the substitution again. Okay, at this place we will put the value of z in terms of r again. Fine, so we will get this value in r. Always remember, you have to find out the solution in terms of small r and small theta. Fine. So similarly, when you have find out this for negative, so here it is c5 cos pz plus c6 sin pz. So this z has to be replaced in terms of r. So we have taken here the substitution like r is equal to e raised to power z. Right. So this implies z is equals to log of r. So you have to put these values. You have to put z equal to log r in all the solutions. Here also it's c9z plus c10. So we have written it c9 log r plus c10. Okay. So we have total 3 sets of solution. Though the possible solutions are u is equals to r into phi, u is equal to r into phi, u is equal to r into phi. The first value r into phi taken from here. The second value r into phi taken from this, then the third value taken from this case. So these are our total 3 solutions, and the general solution will be the sum of the terms of these all. Okay, but whenever you are doing any question based on this, you will take out the solution that will be inconsistent with the physical nature of that problem that will be given to you in the question. Okay, otherwise the general solution is the total sum of these three terms. Okay, so revise this solution once again. Try to find out the solutions for k positive, k negative and k 0. Solve it by yourself. If there is any problem, please ask me. Okay, this is your topic for today. Complete it, properly revise it, and tomorrow we will do the solution of Laplace equation in cylindrical coordinates. Okay, thank you so much, students.